some examples. Let's look at this for example. 46 minus 17 equals 29. This is very simple, but we want to see how it looks like in the binary case. So in binary, 46 equals this number. You can just check it, for example, with a calculator. Let's just make sure, for example, we pick the decimal. We type in 46, and then we pick again the binary. And we get this number. Okay, looks the same? Good. Now the second one, 17. We get this representation in binary notation. Now we go through the 2's complement to get the negative representation of it. And it looks something like this. We take the original number, then we flip every bit. We can see that every bit is flipped. For example, 0 turns into 1, this 0 turns into 1, and so on. Even the last one, 1 turns into 0. Finally, we add 1, as usual, and we get this number, which should represent minus 17 in base 10. This is the 2's complement representation of minus 17. Now, we are just going to add the numbers. Why is that? Because instead of subtracting, we can just add the negation of a number, just like it shows here. And we are going to get this calculation. This is the original number. This is actually 46, like we can see here. It is copied to this number. And the other one, this number, actually represents minus 17. We can see it here. It is copied from this place to this place. And this is just the usual plus operator for binary numbers, and we get this result. As usual, we only consider the lowest 8 bits, because we decide ahead of time that we are going to work in the world of 8 bits. This number that we got actually equals 29 in base 10, which is pretty cool because we really got the correct answer. And we got it only by using the usual plus operator. That usual plus operator, together with the smart interpretation in 2's complement, managed to solve this subtraction question using only addition. I find it very impressive. We can say maybe generally that the plus operator works very well with the 2's complement interpretation. Some other example. This time we are going to look at two negative numbers, minus 15, minus 101, and that equals minus 116. This is not very hard to calculate in your head, but it is more interesting when looking at it in the binary version. So in binary, 15 in base 10 equals this binary representation. And I remind you that we are talking about the 2's complement representation. So minus 15 is going to be this, which is just the bit flipping from the original binary number. Okay, you can see that we flipped every bit. 0 becomes 1, 0 becomes 1. Also, the last one, 1 becomes 0, and so on. Plus 1 as usual, and we get this representation in the 2's complement. This actually means minus 15. We do the same with 101. Also for 101, we get the minus representation in the 2's complement. We did mostly the same thing. We just flipped the bits, add 1, and got this result. So now we have the representation both of minus 15 and minus 101. Both of them in the 2's complement of base 2. Now we can just add those two binary numbers, this number and this number, in the usual way. We just copy them here. You see, this is the first one and this is the second one. And we got this result. As usual, we consider only the lower 8 bits because we decided to live in the world of only 8 bits, we can see that the resulting number, which is this number, begins with 1, which means that it is a negative number. If we would just take this number, for example, we can take the calculator, I pick the binary, and now I just take this number here marked in red, 10001100, and I turn it back into decimal, I get a wrong result. This is not the wanted result. And that is because I haven't yet converted it to a positive number. We have to do the conversion back. Again, we use the 2's complement method. We just flip every bit, as you can see here, and finally add 1. And we get this binary number, and this time this is the right result. We get 116, just like as expected. And as we know that the result was negative, this number actually represents minus 116, which is the right result. Some exceptions. The 2's complement takes positive numbers into negative numbers and vice versa. And we could say that the highest bit is usually flipped after invoking the 2's complement. There are 2 exceptions for that. If we look at the number 0, an interesting thing to see, maybe for example here if we work in the world of 8 bits, that 0 complements himself. 0 is going to complement himself in the world of every number of bits. This is pretty interesting. For example, in the world of 8 bits, when we flip all the bits in 0, we are going to get this number because every 0 is flipped into 1. And then we just finally add 1 and we get this result. As we only consider the lowest 8 bits, we get again 0. So 0 turns into 0 when we invoke the 2's complement. We can also formally say that 0 belongs to the positive numbers because it begins with 0. So this is mostly a strange example. A positive number, when invoked the 2's complement, goes back into a positive number. This is an interesting exception of the general rule that the positives move into the negatives and vice versa when we apply the 2's complement method. Another strange number that complements himself is this number, 1 followed by 7 zeros. This is also known as the most negative number, or sometimes even the weird number. Some people even call this the negative 0. This number also complements himself. We can check it out. For example, for the 8 bits case, we are going to flip every bit. 1 turns into 0, and the rest of the zeros, the 7 zeros, turn into 7 ones. Then we add 1 as usual, and we get again the same weird number. This is an interesting phenomenon. Some graphical view of the numbers, the decimal interpretation in 2's complement representation. What are we actually looking at here? In the lowest row, we can just see all the possible 8 bits binary numbers. We begin from the usual 0 here, and if we count up and we increment 1 every time, we just move from this number to the next one, which is 1, and this is 2, and so on, and we can move on until the last number that we can represent with 8 bits, which is all 1s. And this is what we see if we just look at the bits, but we can at the same time look at the interpretation in 2's complement representation. And what we can see is a bit interesting. The first number, this one, is 0, the next one is 1, and this is 2. And we keep going in the side of the positives until this number, which is 1 0 and then 7 ones, which is the highest positive number. The next number right after it is the most negative number, minus 128. We've seen this number before in the previous slide. And then, in an interesting way, the numbers become less negative as we move on, until we get to this number, the last one, which is consisted of only bits of 1, which is minus 1. There are some other interesting things in this picture. For example, the most positive number, 127, is not as positive as the most negative number is negative. Maybe to put it in another word, the absolute value of the most positive number is lower than the absolute value of the most negative number. We have positive numbers only until 127, but we have negative numbers until 128, which is interesting. We can see here the numbers that complement themselves that we mentioned earlier, 0 and the most negative number. Some philosophy of representation. You now know about at least 2 interpretations for every binary number you see. How could you decide which interpretation is the right one? You might have expected some kind of a very rigorous method to know which one is right in every case, and it might be confusing. There is a bit more philosophical answer. The bits don't know what they represent, and they even don't care. That means that when you look at a group of bits, for example, this group of bits, 8 bits, it could mean minus 116 in base 10, if we look at the 2's complement representation, or it could mean 140 in base 10, if we consider the simple representation, or maybe we should call it the unsigned representation. The meaning of the number is obtained only from your thought about it, and maybe the actions you perform on it accordingly. Let's look at an example. We can look at this addition, which is mostly usual. We just add 2 binary numbers and get a result. There's nothing special in here. We can first interpret it in this method. It might mean that 75 plus 231 equals 306. Why is that? Because 75 equals the first number, 231 equals the second number, and the result equals 306. All of this in the unsigned binary interpretation. This could also mean that 75 minus 25 equals 50. That is because 75 equals the first number, and the second number equals minus 25. The result equals 50 in the signed 2's complement interpretation. It is amazing, but both of these are correct. You see, the bits are just bits. You can look at them in different ways and think different thoughts, but the bits are not going to change. They are just there. In this case also the plus operator is not changing. It's just our thoughts about the numbers that change. Regarding the usage of a calculator to check your results, let me show you what you could do with the Windows calculator regarding signed numbers. This is the calculator in the programmer mode. It might be in the standard mode in the beginning when you just open it, then you can change it to the programmer mode. If we pick here the decimal option, then we could write, for example, some signed decimal number. Just like you would do usually with a calculator. For example, minus 16 equals minus 16. And we have here this result, minus 16. We might want to see it as a binary number. Then we could just click the binary option. And we get this very frightening result of a very long number. And that is because we are above the keyword option. Keyword means 64 bits. This option means I want to live in the world of 64 bits, which might be too much for you at this point. The usual option is byte, for you at least in this course. Byte means 8 bits, just like we are used to. This is minus 16 in the 2's complement. This calculator could be of great help for you if you want to check your results. It just works.